All right, I'm going to do problem number 34, chapter 13. 34 says, Pluto moves in a fairly elliptical orbit around the sun. So this is Pluto's orbit. Here's the sun. That's highly exaggerated. It's not quite that elliptical, but you get the idea. And when it's at its closest approach, which is the perihelion point right here, it gives me that its radius at perihelion is 4.43 times 10 to the 9th kilometers, radius at perihelion. And its velocity at perihelion, we're also given. It's going 6.12 kilometers per second. And we want to know what Pluto's speed is at the aphelion point on here. So velocity at aphelion is what we're trying to find. We are given that the radius at aphelion is 7.3 times 10 to the 9th kilometers from the sun. All right. The good thing about this problem is we have it exactly at perihelion and aphelion point, which means that the velocity vector here is perpendicular to the radius vector, which is here. And same thing here, the velocity vector here is perpendicular to the radius vector. So that I can say the angular momentum, remember, is defined as, for a point source, mass times the velocity times the radius times the sine of the angle. And in both these cases, the angle is going to be 90 degrees. And so I can use the conservation of angular momentum, saying that the initial angular momentum must be the final angular momentum. So this is the initial angular momentum here, which is going to be mvr sine of theta, but this is going to be velocity at perihelion, radius at perihelion, times the sine of the angle. It's going to be equal to mv aphelion times radius at aphelion times the sine of the angle. And they should be technically P and A, but both of those we know are 90 degrees, so those go to 1. And the mass cancels. If you watch my lecture on this, this becomes very simple here. This is an R, by the way. It looks like another V. That's the radius at perihelion. That the velocity at perihelion times the radius at perihelion is equal to the velocity at aphelion times the radius at aphelion. Or we want to solve for this VA, so we're going to say, oh, the velocity at aphelion is just going to be velocity at perihelion times the radius at perihelion divided by the radius at aphelion. Now, the good thing about this, and what makes this easy, is we don't even have to convert to units, because since these are both in kilometers per second, I don't have to convert it because kilometers per second over kilometers per second is going to cancel anyway. And whatever the velocity is here, VA is going to be in the same units, so this will just end up in kilometers per second. So I don't even have to convert anything for this one. If you're doing it as energy, you have to convert, because then you're using constants like G, which only works in MKS units. All right, so we're just going to plug that in. The velocity at perihelion is given to us as 6.12. Radius at perihelion is 4.43 times 10 to the 9th over the radius at aphelion, which is 7.73 times 10 to the 9th. You solve for this and you get the velocity at aphelion is 3.71 kilometers per second. So it's about half of the speed it has when it's at perihelion, when it's out here at aphelion. And that's how you do number 34.